Hello, Professor. How are you? My name's Jeffrey. Today we're going to be talking about the CRJ 200 CF34 3 Bravo 1 engines. Overview on what these engines are. The CRJ 200 uses two high bypass turbofan engines that produce 8,729 pounds of thrust each. So nearly 9,000 pounds of thrust at their normal takeoff. These engines do, however, provide an extra 2% automatic performance reserve that kind of boosts them up over that 9,000 pounds apiece mark. But during normal operations, it's normally just 8,729 is their max thrust. The CF34 has a dual assembly N1 and N2 turbine. The N1 consists of a single fan rotor that is driven through a shaft that is connected to a four-stage low-pressure turbine. The N1 fan consists of 28 titanium alloy blades that are wrapped in Kevlar. That Kevlar is meant to reduce the impact should one of those fan blades have some kind of stress issue where they detach or explode off the fan. It's just meant to kind of contain that, so hopefully the damage doesn't spread to other components in the aircraft, or completely, it's going to damage the engine completely, but completely destroy some other necessary equipment. The N2 consists of a 14-stage axial flow compressor that is connected through a shaft to a two-stage high-pressure turbine. The N2 compressor drives an accessory gearbox that's connected to all kinds of different equipment. The engine oil pump, the N1 control amplifier alternator, the engine-driven hydraulic pump, the engine fuel pump and fuel control unit, and the integrated drive alternate current generator. So the N2 N2 compressor does a lot of different things for the aircraft throughout the several stages of its compression. We'll talk about that here. But first we're going to talk about how the air flows through the engine, because it's actually pretty interesting, and it's something that I learned. So after the air that gets ran through that first N1 stage fan, the airflow then splits into two separate airflow systems. One of those airflow systems is the core air. The core air is the air that passes through the entire engine, is compressed, ignited, and then exhausted through the high-pressure N2 turbine. Then the N1 low-pressure turbine, and then it's accelerated through the exhaust nozzle. The bypass air, this is the interesting part to me, the bypass air literally is what it is. It just bypasses that entire core and is exhausted out the back. However, about 80% of the thrust provided by these engines is provided by that bypass air. Now, that's something that I found extremely fascinating, and I still don't totally understand, to be quite frank with you. But it sounds like all the magic is happening in that N2 compressor. However, all the thrust is coming, or not all of it, but a majority of that thrust is coming from the bypass air. That was pretty impressive to me when I read it. Here's a little diagram that kind of shows what I'm talking about here. So you can see as that air enters the engine, that darker arrow, a little bit darker shaded gray, is just bypassing that entire core altogether. Whereas that air that's coming directly out the back of the engine, that's going actually through the core there. It's getting compressed, mixed with fuel, ignited, and then exhausted out. So that would lead you to your next question, hopefully. How does it get fuel? So the fuel is pumped to the injectors at pressures and flow rates that are necessary for all the desired thrust range. So all the way from full thrust all the way back down to idle just before the fuel shutoff. Fuel is taken from collector tanks by boost pumps. It is then pressurized, heated, filtered, metered, and then delivered to the combustion chamber via the main injectors. Fuel is also used to do several different things in the airplane, right? These engineers did not waste any energy with any of these components. So the fuel also is used to articulate the vertical gyros, the vertical gyro compressor linkages to help cool the engine. Let me back up real quick. The fuel is used to articulate the vertical gyro compressor linkages. This is to prevent the airplane from having compressor fan stalls, which again is probably a whole other lesson, but it uses fuel to do that. It also uses fuel to cool the oil through heat transfer, which I thought was pretty interesting. It uses fuel to actuate and lubricate the fuel control unit servos, and it provides motive flow for the jet pumps. So we talked about fuel being used to cool the engine oil. So what happens is the fuel out on the wings is extremely cold, so it needs to be warmed up. Well, the oil that's circulating through the engine gets very warm, so it needs to be cooled off. So these genius engineers thought, well, okay, why don't we use one to fight the other? So what they do is they vent the, or not vent, but they guide the fuel through a heat exchanger, which is very cold, and then that heat exchanger is filled with this warm oil. So the fuel actually cools down the oil as it passes through this heat exchanger, so that oil can be reused, and the fuel is warm enough to be used inside of the engine and for all these other purposes. After passing through that heat exchanger, the fuel is metered through the fuel control unit, which is a hydromechanical metering device that provides fuel in response to the mechanical commands from the thrust levers. So as the thrust levers go forward, more fuel is delivered through the fuel control unit. As the thrust levers are brought back and slowly back towards idle, less fuel is delivered. And that's mechanical, it's a hydromechanical system. So how does it control speed? So at low thrust settings, the fuel control unit meters fuel to the injectors and regulates the N2 speed. So it's actually taking measurements from N2 and trying to, regulate the speed. However, this produces a mismatched N1 speed between the two engines. So in order to compensate for that, above 79% N1 thrust, with the engine speed switches on, the N1 controller amplifier ECU responds to the N1 speed references, so no longer N2. And this allows the controller amplifier to trim the fuel output to achieve the desired N1 speed. And this actually creates a very symmetrical thrust setting between the number 1 and number 2 engine. So we got to figure out how to start these things. So let's first start by talking about the ignition system. So the ignition system provides DC electrical source for opening the start valve and engaging the air turbine starter, or ATS. The ignition system consists of 2 ignition exciters and 2 ignition plugs, one of each on each side. Ignition A is powered by the alternating current essential bus, while ignition B is powered by the battery bus. Prior to starting, one of the ignitions are armed on the start ignition panel. So then it's time for engine starting. So in the CRJ200, engine starting can be accomplished one of 3 ways. It can be accomplished using APU bleed air. It can use a ground source that will provide high pressure air to the aircraft, or it can use the 10th stage engine cross bleed air from the other engine given it's operating. So starting is controlled again by that start ignition panel, which you're going to see here in just a second. The ignition is armed, like we said before, and the start button is pushed. Once the start button is pushed, bleed air from that 10th stage pneumatic manifold is released and rotates the engine starter. Like we talked about earlier, the engine starter then rotates the N2 compressor through that accessory gearbox. At 20% N2, the FCU provides fuel for combustion, resulting in engine start. Now that's given the throttles are up to idle. Like I said, the throttles are what provide that FCU command to release the fuel. So after engine start, what do these engines do now? Well, of course, they're producing thrust, but they also produce a multitude of other things. And that's done via bleed air. So the N2 compressor provides 7th stage. We talked about there's 14 different stages. So at the 7th stage, bleed air is used for pressurization of oil seals and venting of engine sumps in the lubrication system. Once you get to that 10th stage, you still haven't reached combustion yet, so you're still using nice cool air. The bleed air provides pneumatic supply, it's supposed to be 2, the air conditioning, the avionics cooling, the pressurization system, and is used for engine starting like we talked about earlier. Once you reach to the 14th stage, now you're talking about warm air. So that warm air is used for the anti-ice systems. So it's used for the cowling, the wing, and all the other anti-ice equipment required on the airplane. The 14th stage also provides bleed air to shift the engine, translating cowls and cascades rearward for the thrust reversers. Now that's my overview of the CRJ200's engines. There's a lot of information that was covered. There's plenty of information that wasn't covered. These are very complex engines, but they do a lot of cool things. They're very interesting, and like I say, this is always a learning process. So I'm sure we can get into more as we continue to go down this path of learning aircraft systems. But without my references, and I hope you enjoyed the presentation, and look forward to hearing your comments. Thank you.